Space, vast, mysterious, and beautiful. For many, it's a symbol of exploration and the potential of the human spirit. But there are corners of the universe that, if you were to visit, you might wish you never did. These locations are enough to give anyone a strong dose of astrophobia, a fear of space. Let's dive into some of these awe-inspiringly terrifying regions of space. The Buddha's Void, often referred to as the Great Nothing, is one of the largest known voids in the universe. A void, in cosmic terms, is a region of space that has a significantly lower density of galaxies than the surrounding areas. The Buddha's Void stands out particularly because of its mind-boggling emptiness. This vast expanse spans approximately 330 million light-years across, and while space is generally thought of as being relatively empty, the size and extent of this void are far beyond the norm. To give a perspective on its enormity, our entire Milky Way galaxy is only about 100,000 light-years in diameter. If you were to travel across the Buddha's Void at the speed of light, it would take you 330 million years to cross from one side to the other. But what makes the Buddha's Void even more mystifying is its stark emptiness. While you might expect thousands of galaxies to be present within such a vast space, researchers have found only about 60. That's shockingly sparse. The discovery of the Buddha's Void has challenged our understanding of the universe's large-scale structure. Why? Because it doesn't easily fit into the cosmic web theory, where galaxies are connected by filaments and nodes of dark matter, creating a web-like structure. So how did such a vast void form? There are several theories. One idea is that smaller voids merged over time, resulting in this supersized void. Another theory posits that this region of space experienced a much lower rate of galaxy formation due to variations in the density of matter after the Big Bang. Regardless of the cause, floating within the Buddha's Void would feel like an endless journey through an almost infinite abyss of nothingness. Hot Jupiters are among the most intriguing and unexpected discoveries in the field of exoplanet research. These gas giants bear a resemblance to our own Jupiter in terms of mass and composition, but with one key difference: their blisteringly close proximity to their host stars. Imagine a planet several times the mass of Jupiter, but instead of taking 12 Earth years to complete an orbit around its star, it does so in just a few days. The close orbit of these gas giants means they're exposed to intense heat from their stars, leading them to have daytime temperatures that can soar up to 2,000 degrees Celsius. This is hotter than some stars. This close relationship with their host star also means that hot Jupiters are tidally locked. One side perpetually faces the star, basking in its intense heat, while the other side remains in eternal darkness. This creates a dramatic temperature difference between the two sides. Powerful winds, faster than any on Earth, whip around these planets, transferring heat from the day side to the night side. These winds create storms of unimaginable ferocity, with metallic clouds and rains of molten glass. The existence of hot Jupiters was a surprise to astronomers when first discovered. Traditionally, it was believed that massive gas giants could only form far from their stars, where cold temperatures allowed icy materials to clump together. How did hot Jupiters end up so close to their stars? One leading theory is that they formed farther out and migrated inward over time due to gravitational interactions. Exploring a hot Jupiter would be a lesson in extremes, from its scorching temperatures to its roaring winds and searing storms. A visit to such a planet would expose you to a world where the rules of earthly understanding are dramatically challenged. Magnetars are some of the universe's most extreme objects. Essentially, they're a type of neutron star, remnants left after massive stars explode in spectacular supernova. While all neutron stars are incredibly dense and possess strong magnetic fields, magnetars crank up the intensity to levels almost difficult to fathom. A teaspoon of material from a magnetar would weigh about 1 billion tons on Earth. Picture the entire human population condensed into a sugar cube, and you're starting to get a grasp of the staggering density of these objects. But what truly sets magnetars apart from other neutron stars is their magnetic field. These fields are up to 1,000 times stronger than typical neutron stars. To understand this kind of magnetic might, consider this. If a magnetar were located about halfway to the moon, it could strip the information from all the credit cards on Earth. Magnetars are also dynamic and occasionally unpredictable. They can produce what's known as starquakes, due to the tension between their immense gravity and their magnetic fields. These starquakes can release gamma-ray flares, which are millions of times more energetic than the most powerful solar flares from our sun. Thankfully, no magnetar is close enough to us to pose a threat. However, a gamma-ray burst directed at Earth from even thousands of light-years away could cause significant harm to our atmosphere and possibly even lead to mass extinctions. Black holes, regions of space where gravity is so strong that nothing can escape, not even light, are enigmatic enough on their own. But sometimes, in the vast cosmic dance of the universe, two black holes find themselves in a close gravitational embrace, leading to the awe-inspiring phenomena of binary black holes. In this cosmic tango, two black holes orbit each other, drawn together by their immense gravitational pull. As they spiral closer and closer, they begin to affect the very fabric of space-time itself. This effect is so intense that it sends ripples across the universe, much like how twirling a finger in water would create ripples across the surface. These ripples, known as gravitational waves, were first theorized by Albert Einstein over a century ago and were finally detected in 2015, marking a groundbreaking moment in our understanding of the universe. The eventual merger of these binary black holes is an event of unimaginable power. When they finally collide and become one, the resulting black hole has slightly less mass than the sum of the two original black holes. The missing mass is converted into energy and radiated out as gravitational waves. In some cases, this energy output can be equivalent to the combined light of all the stars in our galaxy. Observing these mergers offers a rare peek into the dynamic and violent relationships that play out in the universe's dark corners. The dance of binary black holes is a testament to the unimaginable forces and phenomena that shape our cosmos. Rogue planets are the true wanderers of our universe, detached and free, traversing the vast cosmic expanses without the gravitational tether of a star. But what makes these celestial bodies so fascinating is the story of their origin and the mysteries they hold. A typical image of a planetary system involves planets gracefully orbiting a star, bound in a celestial dance that spans billions of years. But sometimes this dance can get a bit chaotic. Gravitational interactions, especially in young and turbulent solar systems, can give a planet enough of a nudge to eject it from its home system. This ejection sets the planet on a lone journey through the interstellar void. Size-wise, rogue planets can range from being as massive as Jupiter, the largest planet in our solar system, to being as small as Earth or even smaller. And while they lack the warmth of a star, they aren't necessarily devoid of energy or activity. Some rogue planets might still radiate heat from their formation. This residual warmth, combined with potential internal heat-generating processes, means these planets could harbor subsurface oceans. There's also a possibility that life, at least in some primitive form, might exist on these worlds. If a planet was ejected from its system with a thick atmosphere and enough internal heat, it could provide the necessary conditions for life to persist. Rogue planets, given their solitary nature, are difficult to detect. They don't emit their own light, and without a nearby star, they don't reflect light either. However, astronomers have employed ingenious methods, like gravitational microlensing, where the gravity of the rogue planet acts like a lens, amplifying the light of distant stars. Galaxies are colossal collections of stars, gas, dust, and dark matter. They're the fundamental building blocks of the universe's large-scale structure. But galaxies aren't static. They're dynamic entities, constantly in motion, and occasionally their paths cross in a dramatic event known as a galactic collision. Picture this. Two galaxies, each comprising billions of stars, drawing closer and closer due to their mutual gravitational attraction. As they approach, their shapes start to deform, creating long tidal tails of stars and gas stretched out by the immense gravitational forces at play. Over millions of years, these galaxies can merge into a single, larger entity, often resulting in a new galaxy with a unique shape and character. But here's a fascinating fact. Despite the sheer number of stars in these galaxies, the likelihood of two stars directly colliding during a galaxy merger is minuscule. This is because, relative to their sizes, stars are very far apart from each other. Instead of direct stellar collisions, the real action happens in the interstellar medium, the gas and dust between stars. As galaxies collide, these gases can compress, leading to a burst of new star formation, lighting up the merging galaxies like cosmic fireworks. Our own Milky Way is no stranger to this process. In its history, it's believed to have consumed several smaller galaxies, and as mentioned earlier, in the far future, we're set to collide with the Andromeda Galaxy. While this may sound alarming, remember that this event is billions of years away, and when it does happen, it will be a gradual process unfolding over millions of years, not a sudden catastrophe. The resulting merged galaxy, sometimes whimsically referred to as Milkomeda, will be a new chapter in the ongoing saga of cosmic evolution. In the tapestry of the universe, there are threads that we can see and touch, like stars, planets, and galaxies. And then there are threads that remain invisible and intangible, yet they weave the cosmos together in ways we're just beginning to understand. One such thread is dark matter. Dark matter is aptly named, primarily because it doesn't emit, absorb, or reflect light. Unlike the stars that twinkle in the night or the planets that reflect sunlight, dark matter remains invisible. So how do we even know it exists if we can't see it? The answer lies in its gravitational influence on the things we can observe. When astronomers look at galaxies, they've noticed something intriguing. The stars at the edges of galaxies move faster than they should, if only the gravity of the galaxy's visible matter were at play. This suggests there's something else, something unseen, exerting its gravitational pull. Through such observations and calculations, scientists deduced the presence of dark matter. In fact, it's believed that around 85% of the matter in the universe is dark matter. But here's the twist. Despite decades of searching and countless experiments, we've yet to directly detect a dark matter particle. Various theories suggest what it might be made of. One leading candidate is the weakly interacting massive particle. These hypothetical particles are believed to interact through weak force, one of the four fundamental forces of nature, but not with electromagnetic force, which means they wouldn't emit or absorb light. The quest to understand dark matter isn't just academic curiosity, it's crucial to our comprehension of the universe. This mysterious substance plays a pivotal role in galaxy formation, cosmic structure, and the overall fate of the cosmos. And as always, we hope you enjoyed our video today. Thanks for watching.